Richard Feynman often warned that repeating an answer is not the same as understanding it. Few statements in physics illustrate this better than the familiar claim that nothing can travel faster than light. Most people know the sentence. Very few have ever paused to ask what kind of statement it really is. At first glance, it sounds like a technological limit, as if we simply have not yet built engines powerful enough, materials strong enough, or ideas clever enough to push past it. But that intuition quietly fails the moment we take the statement seriously, because the speed of light does not appear in physics only as the speed of light. It appears in the structure of timekeeping, in the synchronization of clocks, in the way distances are measured, in the rules that decide whether one event can influence another at all. It shows up even when no light is involved. Feynman was drawn to questions like this, not because they were mysterious, but because they were dangerously easy to misunderstand. Why can't we go faster? Is the wrong starting point. The sharper question is, what would have to break if we could? If you stay with this exploration, you will not collect facts about light. You will slowly notice something more unsettling. The universe does not merely limit speed. It uses that limit to hold reality together. To see how a simple sentence about speed turns into a statement about reality itself, we have to slow down the question until it almost feels childish. That was always Feynman's first move. Most of us meet the phrase, "Nothing can go faster than light," the way we meet a road sign. It is printed in the textbook, repeated in documentaries, mentioned in films. After a while, it stops feeling like a claim about the world and becomes more like a slogan. You nod, you move on, you do not argue with the sign. Feynman distrusted that kind of agreement. He knew how easy it is to mistake familiarity for understanding. If you had told him, quite confidently, that nothing can exceed the speed of light, he would probably have smiled and asked something that sounds almost rude in its simplicity. All right. But what exactly stops you? Inside that small question, the entire difference between superstition and physics is hiding. There is a lazy kind of answer that says, because the universe works that way. It feels deep. It is not. It just pushes the question one step further back and paints a fog over it. Feynman had very little patience for this. He was not asking for a mystical reason. He was asking for a mechanism, or at least for a structure, a way that things are arranged so that the limit is not just declared, but enforced. He liked to talk about the game of asking why over and over. You can always keep going, he said, but you cannot go on forever. At some point, the ladder runs out of rungs. You hit a place where all you can honestly say is, we do not know why it is like that. We only know that it is, and that from this starting point, we can explain many other things. For him, that final stopping point had to be earned. You do not get to say, that is just how the universe is, until you have tried every simpler, more precise, and more testable step below it. So when people repeat, nothing can go faster than light, there are really two different questions hiding under the words. One is the numerical question. Why this particular speed? Why this many meters per second? Why this many kilometers each second? Instead of some other number, physicists can relate that value to other constants in nature, but at some stage, that kind of why turns into a request for a reason behind the reasons. That is the sort of thing Feynman would classify under "we do not know." We only know that it works that way in every experiment we have ever done. The other question is more structural. Why is there a maximum speed at all? Why does the universe seem to come with a built-in ceiling for how fast causes can reach their effects? That second question is the one that interested him. It is also the one that quietly rearranges your picture of reality. When Feynman stood at the blackboard in those Cornell lectures on the character of physical law, he did not start with light. He started with gravity. He started with a law that had already been tested for centuries, that could predict the fall of an apple and the orbit of the moon with the same short equation. He wanted his audience to feel something specific, the sense that a good law does not just fit the data. It connects things that used to look unrelated. He described how one simple mathematical rule could account for tides, for the paths of planets, for the shape of star clusters. That was his standard. A serious law of nature does not sit alone. It spreads. It becomes a kind of wiring diagram for reality. By that standard, the speed of light is suspiciously important. It appears in Maxwell's equations, which describe electricity and magnetism. It appears in Einstein's relativity, which tells you how clocks and rulers behave when they move. It appears in the energy of particles, in the behavior of fields, in the way information can be transmitted. It shows up even in places where no literal beam of light is involved, as a kind of conversion factor between space and time. If you are thinking in Feynman's style, this is the moment when you stop being impressed by the number itself and start wondering what kind of structure demands that there be any such limit. This is also where his dislike of empty definitions comes in. He was very sharp about the way we use words to pretend that we have explained something. It is no help to say, the speed of light is the maximum possible speed by definition, and then feel satisfied. That just rearranges the mystery into a new sentence. Instead, his trick was to change the question from, why can I not go faster, to, what would have to break in the framework of physics if I could? That change of perspective turns out to be subtle and brutal at the same time. Imagine you ask a bad question about a familiar film. After watching a story where a ship jumps instantly between stars, you ask, could we build that engine for real? The question smuggles in the assumption that space-time is a stage, like the one in the movie. Flat, obedient, waiting for technology to push harder. Faster engines, stronger materials, cleverer tricks. And eventually, you pass the light barrier, as if it were a sound barrier in the sky. Feynman would tilt his head at that, not because he knew the engineering answer, but because he thought the question starts one level too high. It treats the speed limit as a property of our machines, instead of a property of the coordinates we use to describe events. What if the real issue is not the engine, but the way space and time themselves are arranged? What if the limit is not a wall out there in the distance, but a built-in feature of the grid you are using to label reality? That is where the character of his questioning shows. He would not ask first, can I design a warp drive? But what does it even mean to go faster than light in a world where everyone measures the same light speed no matter how they are moving? Suddenly, the conversation is not about rockets. It is about clocks. About how you decide whether two events are simultaneous. About how you would actually carry information from one place to another and be sure about when it got there. It is tempting to say that the universe has a maximum speed in the same way a car has a maximum speed printed in the manual. Feynman's way of thinking pushes you to see that this is misleading. The more accurate picture is that the universe has a maximum rate at which influence can spread, and that this rate is woven into the geometry we use to describe events. It is not a limit bolted onto the outside of the machine. It is part of the blueprint. This is very different from the way many of us first hear science. In school, you are often given a list of values, a set of definitions. You are told that gravity pulls things downward at so and so many meters per second squared, that light travels at so and so many kilometers per second, that energy and mass are related by a neat little equation. The temptation is to treat these as slogans on a poster rather than clues. Feynman openly complained about that style of teaching. He thought it trained people to memorize answers instead of learning how to ask better questions. The real fun, in his view, was to take a few facts and see how far they could be pushed before they broke, to see which questions made progress and which questions just echoed back at you. In that sense, the speed of light is not astonishing because it is a big number. It is astonishing because once you put it into the theories and chase its consequences, all kinds of other things start to move. Time stretches, lengths contract. The idea of a single universal now dissolves. The notion of cause and effect becomes more constrained and more fragile than common sense tells you. The first trick, then, is not a clever calculation. It is the willingness to admit that the usual question might be the wrong one. Instead of asking, "Why can I not go faster than light?" you ask, "What would have to happen to space, to time, and to causality if I could?" And also, do we see anything in real experiments that would allow those things to happen without contradiction? That second question has teeth. It opens the door to all the work we will walk through later. Measurements of the moons of Jupiter arriving late, interferometers refusing to see any difference in light speed no matter how they are turned, clocks on airplanes disagreeing with clocks on the ground, particles in accelerators taking almost all the energy you give them without gaining much extra speed. In Feynman's language, these are not decorations. They are the tests that tell you whether a way of asking the question actually belongs to physics or to wishful thinking. He liked to say that the real content of a theory is in the things it forbids. A good theory does not just tell you, "Here is what can happen." It tells you clearly, "Here is what cannot happen." Every forbidden possibility is an invitation to experiment. If you ever see one of those impossibilities occur, the theory has to go. From that point of view, "Nothing can go faster than light" is not a piece of dogma. It is a condensed way of saying our best understanding of space and time and fields and particles, when stitched together carefully, forbids influences from outrunning a particular speed. If we ever saw such an influence, the stitching would have to be redone. The question, "What stops you?" becomes very concrete. It is no longer because Einstein said so. It is because if signals could outrun that limit, then different observers would disagree about the order of cause and effect, and the whole structure of relativity would collapse. We are not there yet in the story. We still have to go through apples and moons, through late eclipses of the moons of Jupiter, through a long, quiet afternoon in Cleveland where an interferometer saw nothing when everyone expected it to see a slight shift. But the tone is set. To follow Feynman's way of thinking is to accept that the most powerful step is often the first one. The decision to be dissatisfied with an answer that is too quick. To treat even a famous sentence as a starting point, not as a conclusion. In the end, what will stay with you is not a number of kilometers per second, but a picture, a universe in which tiny points of light around a distant planet once arrived a little bit late, and that small, annoying delay forced us to rethink what it means for anything, anywhere, to happen after something else. The miracle is not that the universe has a speed limit. The miracle is that, by asking the question in just the right way, a human mind can find out. The path to that kind of discovery never begins with a flashy mystery. It usually begins with something so ordinary that it almost feels embarrassing to look at it closely, like watching an apple fall and insisting there is still a question hiding in it. In the stories, Newton is always under a tree. An apple falls. The scene has been polished and repeated so many times that it sounds more like a parable than a piece of physics. But when Feynman talked about Newton, what interested him was not the fruit and not the tree. It was the strange decision to take that everyday fall seriously enough to connect it to the motion of the moon. On the surface, those two motions could not feel more different. An apple drops. You can see it accelerate. Feel it hit your hand. The moon glides overhead, slow and calm, repeating its path in the sky night after night. One belongs to the realm of daily life. The other feels remote, almost decorative. Newton's move was to refuse that separation. He asked a question that seems obvious only in hindsight. If gravity is what pulls the apple downward, could that same pull be what keeps the moon in its orbit? If the Earth's attraction were suddenly turned off, the apple would float, so would the moon. If the attraction is kept on, both must be falling all the time. The apple's path is cut short by the ground. The moon's path is never cut short. It is falling around the Earth, always aiming inward, always missing, circling endlessly. The difference between falling down and orbiting becomes a matter of geometry rather than a matter of category. Feynman loved this kind of unification. To him, the power of a law of nature shows up not just in its ability to fit data, but in its willingness to erase artificial boundaries in our thinking. A really strong law does not care whether you are in a garden or under the night sky. It does not care whether you are watching a tide rise at a harbor or tracing the path of a comet. It gives you the same simple structure each time, and you have to adjust your intuition to match it. What makes Newton's law so important for our story about speed is not the specific formula, written in chalk. It is the habit it teaches. If a law works in one regime, you are allowed to trust it enough to extend it and see where it breaks. If it survives the stretching, you keep it. If it tears, you learn something even more interesting. In Newton's time, there was no notion yet of a cosmic speed limit, but he had already given later physicists the tool they would need to even ask that question. Confidence that a single quantitative rule, carefully tested, could bridge enormous differences in scale. He began from a very modest measurement. On the surface of the Earth, if you drop an object and ignore air for the moment, you find that its speed increases by the same amount each second. That steady increase can be described by a constant rate of acceleration. The exact value is not what matters here. What matters is that this acceleration seems to be the same whether the object is a stone, a ball, or a block of wood, as long as you account for air resisting them. From that sameness, Newton dared to extrapolate outward. Suppose the moon is falling with the very same rule, only sideways fast enough that it keeps missing the Earth. If you know how far away the moon is, you can calculate how much its path should bend inward in the time it takes to move a small step along its orbit. That bending is just another way of talking about how much it falls in that time. There is a quiet audacity in this. You take a number extracted from a little patch of space near the ground, and you apply it to a distant, untouchable body in the sky. You are betting that the universe does not secretly switch rules between here and there. Feynman liked Newton partly because of that nerve. He described him as someone who did not just notice a pattern but was willing to push it to its logical conclusion, even when that meant tying the fate of the moon to the drop of an apple. It set a standard. If later physicists were going to claim that a certain speed is the ultimate limit, they would have to show that this limit behaves in the same stubbornly consistent way across wildly different situations. The story from apples to moons also shows something else that mattered deeply to Feynman: the way a law, once trusted, becomes a tool for discovering new laws. Once Newton's gravitational law had survived its first round of tests, it turned into a measuring instrument. Astronomers began to treat planets and moons as moving markers in a grand experiment. If the law predicted their motions perfectly, fine. If not, the discrepancies were not an embarrassment. They were clues. This is how the whole question of the speed of light quietly entered the scene. Long after Newton, as telescopes improved and observations multiplied, astronomers made timetables for the motions of Jupiter's moons. These little points of light winked in and out as they passed behind the planet. With Newton's law in hand, you could predict those eclipses ahead of time. The moons became celestial clocks. When those clocks failed to keep perfect time, the first suspicion was not that gravity had suddenly changed its mind. The law had already earned a certain level of trust. Instead, people began to consider the possibility that something else was interfering. Perhaps it was not the motion of the moons that was inconsistent, but the travel time of the light bringing news of their positions to Earth. That particular step belongs to another part of this story, but the pattern is set here, in the way gravity taught us to lean on a law. Feynman emphasized this pattern in his Cornell lectures on the character of physical law. He chose Newton's gravity as his main example, not because it was the final truth, but because it was such a clear instance of how a good theory behaves. It is simple to write down. It explains a large variety of phenomena. It makes specific, risky predictions. And, importantly, its success in one domain gives you the courage to use it as a baseline when you see something odd in another. In those lectures, he described tides in a way that makes this concrete. The Earth rotates under a gravitational field that pulls differently on the near and far sides of the oceans. The result is not just a single bulge of water facing the moon, but two, one on each side. From that same law, you get an explanation not only for the fall of an object, but for the daily breathing of the seas. The same rule helps you understand why the Earth is not a perfect sphere, why its equator bulges, why the paths of planets are ellipses and not arbitrary loops. It is a single thread woven through many very different experiences. When you look at the later history of physics through that lens, the fascination with the speed of light starts to make more sense. Physicists are not obsessed with that limit because they like bright beams. They are obsessed with it because, much like Newton's gravitational constant, it keeps showing up in equation after equation, linking phenomena that would otherwise seem unrelated. The moral from the gravity story is this: when nature offers you such a unifying parameter, you are allowed to treat it with a special kind of seriousness. You use it to test your own understanding. If you ever found a situation where gravity failed dramatically, where planets wandered without regard to the law, you would not quietly adjust the data. You would say, something is wrong here, and whatever is wrong is probably more interesting than anything we have seen so far. By the same token, if anyone ever found a genuine signal outrunning light, in a way that cannot be explained by any bending of space-time or clever geometry, it would not just be a cool piece of engineering. It would be a crack in the conceptual wall that holds together relativity, field theory, and our entire account of causality. The way we learn to trust gravity is what gives statements like that their weight. There is also a more philosophical lesson that Feynman drew from Newton's success. A law of nature, in this style, is not a description of everything that happens. It is a concise rule that says, given these conditions, here is how certain quantities change. The law does not care what you call the objects, or what meanings you project onto them. It only cares about measurable relationships. That attitude protects you from a subtle trap. When people say, the universe works as it does because of a plan, or a purpose, they are reaching for a level of explanation that physics, as Feynman understood it, does not promise. The law for gravity does not tell you why masses attract in any ultimate sense. It tells you exactly how the attraction behaves, so reliably that you can bet satellites, bridges, and clocks on it. He thought that was enough, more than enough. It was already miraculous that such a compact mathematical pattern could predict phenomena across such a vast range of scales. To demand a metaphysical justification on top of that sometimes felt to him like wanting a second kind of certainty for which we have no clear standard. This restraint will matter later, when we come back to the question of why any speed limit exists at all. At some point, we will hit the same wall Newton hit. We will be able to say, here is the structure, here are the consequences, here is the way experiments confirm it, and we will not be able to say much more. The honesty lies in recognizing that point and not pretending to have moved past it. For now, the important thing is the habit of mind that gravity taught us. Trust a law only after it has survived serious attempts to break it. Once it has, use it aggressively. Extend it. Combine it with other laws. Let it help you notice anomalies. Then, when something small refuses to fit, when a moon arrives a few minutes late, when a clock ticks a fraction of a second off, when an interference pattern fails to shift, you know you are not just looking at noise. You are looking at a potential doorway. The first of those doorways into the speed limit question did not open in a laboratory full of lasers. It opened in the 17th century, in the meticulous notes of an astronomer watching tiny shadows move across the face of Jupiter, trusting Newton's gravity enough to be troubled when the universe seemed to run a little slow. Before we can follow him there, we have to sit for a moment with the quiet boldness it took to go from a falling apple to a falling moon, and to believe that one law could hold the two together. The doorway opens with something as small as a delay on a clock. Not a broken machine, not a failed theory, just a tiny, nagging mismatch between when you expect a shadow to appear on Jupiter and when it actually does. In the late 17th century, a Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris. His task was not to overthrow intuitions about reality. It was practical. The more precisely you could predict the motions of Jupiter's moons, the better you could refine navigational tables and understand the mechanics of the solar system. Among those moons, one in particular, Io, became his focus. Io disappears and reappears as it slips into Jupiter's shadow and out again. Each eclipse is like a tick of a celestial clock. Once you know its orbital period, you can calculate when the next disappearance should happen. And the next, far into the future. With Newton's law of gravity as a guide, the pattern should be regular. Even before the law was fully written in the form we now know, the orbital motion itself was well enough understood to treat the system as predictable. Romer and his colleagues spent years noting the times of these eclipses. Night after night, through the changing seasons, they watched the little point of light vanish behind the planet and emerge again. They wrote down their measurements against the ticking of pendulum clocks, against the cycles of Earth's own rotation. At first, everything seemed fine. The eclipses came nearly when expected. But as the months and years passed, a pattern slowly emerged. When Earth and Jupiter were moving closer together along their orbits, the eclipses appeared to happen slightly earlier than predicted. When the two planets were moving farther apart, the eclipses arrived late. The difference was not dramatic. It was on the order of minutes. But it was systematic. Across many observations, the delay for the late eclipses grew until it reached roughly the span of time it takes to boil an egg and wait impatiently at the stove. About 8 minutes. Then, as the geometry changed again and Earth swung around its orbit toward Jupiter once more, the discrepancy shrank. This was not random noise. Something was being revealed, but only if you trusted that the Jupiter system itself was not misbehaving. Here is where the lesson from gravity matters. If you allow yourself to suspect the law every time a measurement is inconvenient, you never learn anything new. If, instead, you treat a well-tested law as a reliable base, then discrepancies become arrows pointing to new phenomena. Romer chose the second path. He assumed that the moons of Jupiter were keeping good time. Their motion, governed by gravity, was not speeding up or slowing down for mysterious reasons. The irregularity must lie somewhere else. He considered the geometry. When Earth is on the side of its orbit closer to Jupiter, the distance between the two planets is smaller. When Earth has sailed to the far side, the distance is larger by roughly the diameter of Earth's orbit around the Sunday. If the eclipses themselves are truly periodic, but their observed times shift with that distance, there is a simple, if startling, explanation. Light must take time to travel. As Earth moves away, the light from the eclipses has farther to go before it reaches the telescope in Paris. Each successive signal is delayed a little more. By the time Earth is as far from Jupiter as its orbit allows, the accumulation of extra travel adds up to those several minutes of delay. When Earth moves back toward Jupiter, the process reverses. The signals have less distance to cover. The observed eclipses creep ahead. Romer presented this reasoning to the French Academy of Sciences in the year we now call 1676. He did not speak in terms of electromagnetic waves or quantum fields. Those ideas did not exist yet. He spoke instead in the simplest possible terms. The evidence shows that light does not move infinitely fast. It has a speed, large, but finite. His estimate of that speed, made with 17th century instruments and methods, was not precise by modern standards. From the total delay accumulated as Earth moved across its orbit, he inferred that light needs on the order of many minutes to cross the diameter of that orbit. From that, you can infer a time of roughly several minutes for light to travel from the Sun to Earth. Christian Huygens later did a similar calculation and wrote down a value for this travel time that is only a little larger than the one we accept today. It is easy to be distracted by the arithmetic and forget the conceptual shock. Before Romer, many natural philosophers had treated light as effectively instantaneous. Whatever light was made of, whatever its nature, the distance between an object and the eye was not thought to impose a noticeable delay. You look at Jupiter, and in that act of looking you assume without quite saying it, that you and the planet share a single now. After Roma, that assumption is no longer safe. The observation that Jupiter's moons can run minutes early or late, purely because of changing distance, means that the act of seeing is always an act of receiving old information. When you look at Jupiter, you see it as it was some time ago. When you look at the Sun, you see it as it was roughly 8 minutes in the past. When you look at distant stars, you are watching histories, not live broadcasts. Feynman liked this story, partly for its drama and partly for its modesty. There is no great experiment here in the heroic sense. No gigantic machine. No sudden explosion of data. There is just the patient accumulation of timings, the stubborn trust in celestial mechanics, and the willingness to believe the pattern even when it pushes against entrenched intuitions. In his lectures, he would strip the story down to the essentials. Suppose, he would say, that you have a system whose dynamics you understand very well. Jupiter and its moons. Newton's law, the ability to compute when Io should disappear and reappear. Suppose further that you notice a regular drift in the times, correlated not with any internal property of the system, but with your own changing position in space. Then, the simplest conclusion is that information does not reach you instantly. Some finite speed is involved. And once that speed is established as a real physical quantity, not a matter of convention, it can start to appear in other parts of physics. After Roma, the speed of light is no longer an abstract possibility. It is a number you can, in principle, measure and refine. In the following centuries, other experimenters would do exactly that, using rotating mirrors, toothed wheels, and later, precise electronic methods. Fizeau, Foucault, Michelson, and many others carried the work forward. Each generation reduced the uncertainty, but they were all, in a sense, moving along a path that a Danish astronomer had traced, with Jupiter's moons and a pendulum clock. What Feynman emphasized, though, was that the really deep shift is not about how accurately we know that speed. It is about what kind of thing we understand it to be. In the Roma era, it is still natural to think of the speed of light as a property of light alone. It is how fast this particular kind of stuff travels. Just as you might say that sound travels at so many meters per second in air, or that a ship moves at so many knots through water, you might say that light moves at such and such a speed through the ether, the hypothetical medium of the time. But even at this early stage, there is a hint of something more structural. The fact that you can use a gravitational clock to discover the speed of light suggests a kind of entanglement between different parts of physics. Gravity sets the orbits of Jupiter's moons. Those orbits give you a schedule. The schedule lets you see discrepancies. The discrepancies reveal the travel time of light signals. A law in one domain exposes a parameter in another. Feynman liked to point out how astonishing it is that you can learn about the fundamental limitations of information transfer in the universe by watching tiny points of light blink in and out around a distant planet. No satellites, no lasers, no spacecraft. Just the sky itself, behaving as a laboratory. There is also a subtle existential twist hidden in Roma's conclusion. If every view of the universe is delayed, then there is no such thing as a God's eye snapshot of what is happening now everywhere. The very idea of a global present tense becomes suspect. You can define a now for your own location and your immediate surroundings, but as you reach out across astronomical distances, now phrase into a set of surfaces in space-time, each defined by how long light has taken to reach you. Roma would not have put it in those words. Einstein had not yet written down the special theory of relativity, with its precise rules about simultaneity and the relativity of time intervals. But the seed is there. The discovery that light takes time to travel is the first crack in the idea of a perfectly shared, universal present. From Feynman's point of view, this is the moment where a simple fact about speed begins to touch the structure of reality. The finite travel time of light is not just a curiosity. It is the reason why astronomy is always historical. It is the reason why any notion of causality must respect a maximum rate at which influences can propagate. Once you accept that limit, even in its rough, 17th century form, you are one conceptual step away from recognizing that the speed of light is not just about light. It is about the geometry of space-time. You can feel the style of reasoning that Feynman admired in Romer's work. It is not mystical. It does not pretend to know more than it does. It takes a small, concrete discrepancy and follows it stubbornly to its source. When the answer looks strange, it does not turn away. It would have been easy, at the time, to dismiss the timing differences as errors in observation, as irregularities in the behavior of the moons, or as quirks of the instruments. That would have been safer. It would have avoided the need to rethink something as basic as the speed at which sight itself operates. Instead, Romer trusted his data enough, and the gravitational picture enough, to accept the uncomfortable conclusion. Light is fast, but not infinitely fast. Every glimpse of the universe comes with a built-in delay. Later, when we speak about the speed of light as a cosmic speed limit, this is the foundation we are standing on. Without Romer's insistence that light speed is finite and measurable, the later questions would hang in the air. You cannot ask why nothing can outrun light until you know that light itself does not outrun everything. There is a quiet irony here. Many people hear the story of finite light speed and shrug. Of course, it takes time for things to travel. What else would you expect? The shock has worn off. But if you follow the line of thought back to its beginning, to a 17th century astronomer tracking the tiny shadows of a distant moon, you can recover some of that original strangeness, the realization that vision itself is always late, that you never quite see the world as it is, only as it was, that even your most immediate sense of now is built from signals that have had to hurry at a fixed and finite pace through the dark. From that point on, the question that opened our story starts to change shape. When you say, "Nothing can travel faster than light," you are no longer thinking about engines and rockets first. You are thinking about how any observer, anywhere, must live inside this delay, and how the universe uses that fixed speed as the outer boundary of what can be cause and what can be effect. The next steps in this chain will make that boundary more explicit and more unforgiving. But the first sign of it was simply this: a clock in the sky running a few minutes slow, and a human mind willing to believe that the delay was real. The idea that every glimpse of the universe arrives late is unsettling enough, but things become stranger when you build a machine designed to catch that lateness in the act, and the universe refuses to give you even the smallest shift. By the end of the 19th century, physicists thought they had a reasonably clear picture of what light was. Maxwell's equations had woven electricity and magnetism into a single theory of electromagnetic waves. Those waves had a particular speed, the same one Romer had inferred long before. The natural next question, in the language of that time, was simple. Waves in what? Sound needs air or water or some kind of material. Ripples on a pond need the pond. It felt almost self-evident that light, as a wave, would need a medium as well. That hypothetical substance was called the luminiferous ether. The ether, as imagined, filled all of space. It had to be rigid enough in some sense to support incredibly fast vibrations, and yet tenuous enough not to slow down planets and comets as they moved through it. It could not be smelled, seen, touched, or bottled. But it was a comforting thing to picture. Waves need something to wave in. If such an ether existed, the Earth would not be at rest in it. Our planet orbits the Sunday. The solar system itself moves through the galaxy. From the point of view of the ether, Earth should be drifting along like a ship through water, or like a person walking through rain. That image immediately suggests a way to test the idea. If the Earth is moving through the ether, then the speed of light should not look exactly the same in all directions when measured from Earth. Along the direction of motion, the light should be slowed a little by the ether wind, or sped up, depending on how you set up the experiment. Across the direction of motion, the speed should look slightly different. The mismatch would be tiny, but not impossibly tiny. Given the sensitivity of late 19th century optics, it might just be measurable. If you could detect it, you would have direct evidence of the ether's reality. If you could not, the idea would be in trouble. Albert Michelson, working first in Berlin and later in the United States, took this challenge personally. He had already attempted a measurement of the speed of light with a rotating mirror and achieved remarkable precision for his time. The ether problem attracted him for the same reason. It offered a concrete, sharp prediction. If the ether was real, the effect should be there. If the effect was absent, no amount of hand-waving would rescue the concept. Michelson joined forces with Edward Morley in Cleveland. Together they built what became one of the most famous instruments in physics. An interferometer mounted on a massive stone slab, floating on a pool of mercury so that it could be rotated with minimal friction. The principle of the device is simple in spirit, if intricate in detail. You split a beam of light into two parts and send them along perpendicular paths, like two arms of a cross. The beams reflect off mirrors and then recombine. If the travel times along the two paths are exactly the same, the peaks and troughs of the waves line up in a particular pattern of bright and dark fringes when you look at them through a telescope. If one path is even slightly longer in time than the other, the pattern shifts. The number of fringes that slide past as you rotate, the device tells you how much the relative travel time has changed. Now imagine that the whole apparatus is drifting through the ether. When the cross-shaped device has one arm aligned with the direction of motion, light traveling along that arm should be moving with and against the ether wind in turn, taking slightly more time than the light traveling along the sideways arm. Rotate the device by a right angle, and you swap the roles. The difference between the two orientations should show up as a shift in the interference pattern. The calculation is sobering. The expected shift is small, but not absurdly small. With the level of stability and sensitivity available to Michelson and Morley, a careful experiment over many rotations should have revealed it. This is the setup that Feynman loved to talk about, because it exemplifies a very particular kind of courage in physics. You pose a question in such a way that nature can answer clearly yes or clearly no. You do not build an experiment that can be interpreted in many ways. You build one that, in principle, leaves you no room to hide. In the summer of that famous Cleveland run, Michelson and Morley watched the fringes. They rotated the massive stone table. They waited for the delicate pattern to slide. They recorded careful measurements under different conditions, at different times. The pattern did not move as expected. There were tiny fluctuations, the kind that any real instrument will have, but no systematic shift that matched the prediction of an ether wind. Within the sensitivity of their device, the speed of light appeared to be the same along both arms, regardless of the orientation of the apparatus. It is hard to overstate how disappointing that must have been on a personal level. They had built a beautiful machine. They had framed a sharp hypothesis. They were, in effect, asking the universe for a sign of the medium that everyone believed must be there. The universe replied with indifference. Feynman, many decades later, read this as a kind of triumph, not for the ether, obviously, but for the way science handles being told no. The Michelson-Morley result did not confirm a beloved theory. It simply failed to see what that theory strongly suggested should be visible. There are several ways to react to such a null result. You can decide the experiment was not sensitive enough and try again with better equipment. You can adjust the theory in small ways, adding complications to hide it from the test. You can insist that something subtle went wrong with the apparatus. All of those responses occurred in the years following the Cleveland experiments. Some physicists tried to argue that the Earth might be dragging the ether along with it in a particular way. Others suggested that the length of the instrument arms might be changing imperceptibly in response to motion through the ether, conspiring to cancel the very effect the experiment was designed to reveal. Out of that second line of thinking grew the idea now called Lorentz contraction, the notion that objects physically shorten along the direction of motion through the ether, just enough to keep the interference pattern still. It was a clever rescue. It preserved the ether at some cost, in simplicity. From the perspective Feynman later took, this is a classic example of how theories can be protected from falsification by piling on adjustments. You can always add a subtle influence, an invisible mechanism, a compensating effect, just where you need it to keep your favorite idea alive. The price you pay is that the theory becomes bloated and less predictive. It forbids fewer things. Nearly any result can be interpreted as consistent with it. What makes the Michelson-Morley story powerful in Feynman's hands is that it shows an alternative attitude. You can instead take the result at face value and ask whether your original question was the right one. The question had been, in effect, how fast is the Earth moving through the ether? The experiment's refusal to see any difference suggested a more radical possibility. Perhaps that question has no answer, because the ether does not exist. That sounds obvious in hindsight. At the time, it was anything but. The ether had become woven into the way people pictured electromagnetic phenomena. It was hard to imagine waves without something waving. To give up the ether was to give up a comforting picture. Feynman liked to emphasize that Einstein's special theory of relativity, published in the first decade of the 20th century, can be read as an act of intellectual honesty about this situation. Rather than patching the ether idea, Einstein took seriously both the form of Maxwell's equations and the empirical fact that experiments like Michelson-Morley saw no difference in light speed, with orientation, or with the Earth's motion. He proposed something simple and extreme. The speed of light in vacuum is the same for all observers in uniform motion, regardless of their state of motion or the motion of the source. There is no ether wind to measure because there is no preferred frame of rest for space. The price he paid, conceptually, was that space and time could no longer be treated as absolute backdrops. To preserve a fixed light speed, he allowed the measurements of length and duration to depend on the motion of the observer. Time could dilate, lengths could contract, simultaneity could become relative. In this view, the Michelson-Morley experiment did not tell us that there is some weird conspiracy of physical deformations hiding the ether. It told us that the universe is less accommodating to our intuitive pictures than we had hoped, and that the speed of light is not a speed measured against a hidden medium, but a structural constant in the geometry of space-time. Feynman's appreciation of this moment has a moral quality. It is not just about cleverness. It is about a willingness to listen when an experiment says nothing. A strong result is not always a big spike on a graph. Sometimes it is the stubborn flatness of a line that refuses to budge. He often returned, in his discussions of the philosophy of science, to the idea that the most valuable theories are those that rule out a lot. They tell you clearly, if you see this, I am wrong. Michelson and Morley devised such a test for the ether concept. The test was passed by reality in a way that the theory could not gracefully accommodate. There is a quiet connection here back to Roma and Jupiter's moons. In both cases, the crucial move is to trust your law enough to use it as a ruler. Roma trusted the gravitational clock of Io enough to blame the delay on light. Michelson and Morley trusted wave optics and their interferometer enough to blame the lack of motion in the fringes on the non-existence of the ether, rather than on subtle failures of the device. From that vantage point, the speed of light takes on an even more peculiar role. First, it appears as a finite travel time, deduced from astronomical delays. Then, it shows up with a fixed value in the equations of electromagnetism. Then a precision experiment, built to reveal a background medium against which that speed might vary, stubbornly fails to see any variation at all. By the time Einstein steps into the story, the number itself has begun to look less like the speed of a particular substance and more like a property of the stage. It is the same no matter who measures it, no matter which way you set up your apparatus. As long as you are not accelerating, that kind of invariance is rare and precious. It marks out something deep. Feynman loved invariants. He treated them as the clues that guide you through the maze. Whenever you find a quantity that stays the same for all observers or in all processes, you have probably stumbled onto something structural. The Michelson-Morley experiment is, in his telling, where the ordinary notion of speed begins to crack. In daily life, you can always ask, speed with respect to what? The ground, the air, the water, in a universe without ether, and with a fixed light speed for all inertial observers. That question starts to lose its footing. Relativity replaces it with a web of relationships between different observers, each with their own clocks and rulers, all agreeing on the outcome of experiments in a way that honors the same constant. When people later ask, almost casually, "Why can nothing go faster than light?" They are often imagining a universe where the Michelson-Morley experiment gave the answer everyone expected, where there was a detectable ether wind, where light speeds could be added and subtracted against a fixed background. We do not live in that universe. We live in a universe where an exquisitely sensitive stone table floating on Mercury was turned patiently through many angles, and the pattern of light on a screen refused to slide. The absence of motion in those fringes helped kill a whole way of talking about space. It was one of the first clear signs that the question, "faster than what?" would have to be asked in a new language. In that quiet refusal, the speed of light took one more step toward becoming what Feynman wanted us to see it as. Not a speed you might someday outrun with better technology, but a speed that the structure of reality itself is built around. The strangest part is that nothing dramatic happens to light in this story. The drama is all on our side, in what we are forced to give up about space and time so that the speed of light can stay still. Einstein's move, which Feynman admired so much, was brutally simple in its statement. Take Maxwell's equations and the stubborn facts from experiments like Michelson-Morley at face value. Accept that, for any observer moving without acceleration, the speed of light in empty space comes out the same. Then refuse to hide that fact inside extra mechanisms like ether winds or secret contractions. Instead, pay the price where it hurts most, in your picture of time and distance themselves. In the old Newtonian world, time was the easy part. There was one cosmic clock, ticking steadily, the same everywhere. Two events either happened at the same moment or they did not, and everyone would agree on that judgment, no matter how they were moving. Space was a rigid stage, time was a universal metronome, and velocities simply added. If you walked forward in a train, your speed relative to the ground was just the speed of the train plus your speed along the aisle. Nothing in that picture seemed negotiable. The experimental facts pushed Einstein to a different conclusion. If light refuses to speed up or slow down for any observer, then the simple rule for adding velocities cannot be quite right. You cannot just say, light from a moving train goes at the speed of the train plus the speed of light, because that would immediately allow observers to see different light speeds. The constant has to stay constant. Something else must give. He chose to let time and space themselves bend. Feynman liked to explain this as a kind of accounting trick that the universe performs perfectly. Imagine that each observer has their own set of rulers and clocks. When they compare notes after moving relative to each other, they do not necessarily agree on how long an interval lasted or how large a distance was. But they do agree on the outcome of physical experiments, because nature quietly adjusts their measurements so that the speed of light and certain deeper combinations of time and distance remain the same. Time dilation is the first and perhaps most unsettling example. According to special relativity, a clock that moves relative to you will tick more slowly than your own. This is not an illusion caused by bad signals or faulty perception. It is a feature of how time behaves when you compare different paths through space-time. Suppose you send an astronaut on a long journey and they travel very fast, a significant fraction of the speed of light, before turning around and coming back. On their own ship, their heart beats normally. Their coffee cools at a familiar rate. Their wristwatch moves from 1 second to the next with its usual comforting rhythm. According to every local check they can do, nothing strange is happening. But when they return and step onto Earth again, they will have aged less than the people who stayed behind. Their clock will show fewer ticks between departure and return than the identical clock you kept at home. Time along their path has genuinely stretched. It is not that their clock malfunctioned. It is that, for them, less proper time elapsed between those two events. Feynman's way of saying this is that the universe allows different observers to use different slices of spacetime as they move, and those slices can have different lengths in time. Yet, when both observers measure the speed of light along their own paths, they always get the same value. Time has bent just enough to protect that invariance. Length contraction is the matching effect on space. If you watch a fast-moving object fly past you, Special relativity says that, in the direction of its motion, it will appear shorter than it is in its own rest frame. A meter stick rushing by does not keep the same length in your measurement as it does in the measurement of someone riding with it. Once again, nothing has been smashed or crushed in the ordinary sense. It is the way space coordinates must adjust if the speed of light is to remain the same across all inertial frames. These ideas can be wrapped in equations called Lorentz transformations, which relate the coordinates and times measured in one moving frame to those in another. Feynman appreciated the mathematics, but he always tried to bring the discussion back to physical meaning. The core point, for him, was that the universe seems willing to sacrifice the absoluteness of time and distance as independent notions in order to keep the combination that determines the speed of light absolutely fixed. In more poetic terms, you could say that time is surprisingly flexible. It will slow down for moving clocks, and space will compress along their direction of travel, all to make sure that no one ever sees light go faster or slower than the same constant value. This is not just a philosophical posture. It shows up in experiments that do not care at all about our feelings for Newtonian time. One of the most direct checks came in the early 1970s, when Joseph Hafele and Richard Keating took very accurate atomic clocks and flew them on commercial airliners around the world, once eastward and once westward. When the clocks were brought back together and compared with a reference clock that had stayed on the ground, they disagreed by amounts that matched the combined predictions of special and general relativity. The flying clocks, which had moved quickly and spent time higher in Earth's gravitational field, had experienced time differently. You can think of these flights as a very gentle version of the astronaut story. The speeds involved were tiny compared to light, and the time differences were tiny as well, measured in nanoseconds and microseconds. But they were real. They were measured. The universe had, in a small but definite way, bent time and distance to preserve its own internal bookkeeping. Feynman would point to these results not as proofs that we fully understand time, but as solid evidence that the strange rules of relativity are not optional. They are built into the way the world works, even when we are just sitting in an airport. The same effect operates continuously in systems we rely on every day. The global positioning system consists of satellites orbiting Earth, each carrying atomic clocks and broadcasting their time. Your phone or car receiver listens to multiple satellites at once and calculates its position from the delays in those signals. The catch is that the clocks on the satellites do not tick at the same rate as clocks on the ground. They are moving relative to you, and they are higher up in Earth's gravitational field. Both effects cause their time to run at a slightly different pace. Engineers cannot ignore this. They incorporate the relativistic corrections into the design and operation of the system. If they did not, the positions computed would drift by kilometers each day. The very fact that your map application can tell you which side of the street you are on is quiet evidence that time dilation and gravitational time bending are part of the practical fabric of modern life. Feynman delighted in these crossovers between deep theory and mundane technology. For him, they were a kind of answer to the worry that relativity is just a clever redefinition of words. If the theory were only semantics, it would not have teeth in machines that must work to strict tolerances. The universe itself seems to be enforcing the same equations that textbooks write down. Behind all of this is a deeper geometric picture. Special relativity replaces the old separation between three-dimensional space and one-dimensional time with a four-dimensional space-time, in which events are points and the interval between them has a specific structure. The speed of light is not just a number in that setting. It defines a sort of conversion factor between space units and time units, much as a fixed exchange rate converts one currency into another. When you draw space-time diagrams, with time on one axis and space on another, the paths of light rays always lie along lines at the same angle. No matter which inertial observer you choose, their axes tilt relative to one another in such a way that those light paths remain at that fixed angle. The transformations that relate observers are precisely those that keep the speed of light invariant and preserve the space-time interval. This is what Feynman meant when he said that the universe does its accounting. It is as though there is an underlying quantity that must add up correctly from every viewpoint, and time and space are willing to warp their individual values as needed, as long as the combined balance sheet stays intact. The speed of light is one of the constants etched into that accounting system. An interesting side effect of this structure is the way it reshapes the concept of now. In relativity, two events that seem simultaneous to one observer may occur in different order for another observer moving at a high speed relative to the first. There is no unique global slicing of space-time into moments that everyone agrees on. Instead, each observer carries their own notion of present, defined by the surface of constant time in their frame. Feynman had little patience for vague mysticism about this. He did not claim that relativity abolishes time or proves that everything is fixed in some metaphysical sense. He simply insisted that the mathematics and experiments show that simultaneity is not an absolute concept. Once again, the universe is choosing consistency over comfort. To protect the invariance of light speed and the causality structures built around it, it lets go of the simple picture of a universal ticking present. All of these adjustments make the light speed limit look very different from a speed limit on a highway. A road sign is an external rule, imposed from outside. In principle, a car can exceed it if the driver is willing to pay the fine or take the risk. The physics of the car does not prevent it. There is no law of mechanics that says you may not exceed this number. The cosmic speed limit is of another kind. It is not a law laid on top of the dynamics. It is woven into them. When something with mass is accelerated, the effort does not simply translate into more and more speed in a linear way. Near the speed of light, pushing harder yields diminishing returns in velocity. The extra energy goes into changing the relation between time and space along the object's path, rather than into increasing its speed past the limit. You can see hints of this in particle accelerators. Protons in machines such as the Large Ring near Geneva are pushed to speeds so close to the speed of light that, if you measured them classically, you might say they are within a hair's breadth of that maximum. Pouring in more energy does not make them outrun the light beam traveling alongside them. It just increases their energy and their effective inertia, making them harder to deflect or speed up further. The limit remains untouched. Feynman liked to describe this as a wall that is not quite a wall. You never hit a barrier with a crash. You just find that the world becomes more and more reluctant to translate your effort into more speed. In terms of the mathematics, the velocity addition formula of relativity ensures that no matter how you combine speeds less than light, the result is still less than light. The structure of space-time bends the rules of addition to protect its own constant. There is a kind of humility hidden in this design. The universe is not giving us a finish line we might one day cross with enough ingenuity. It is giving us a framework within which motion and cause and effect make sense at all. The light speed limit is tied to the very possibility of having a consistent order of events, of being able to say that one thing happened before another in a way that all observers can agree on when it really matters. Feynman's way of thinking resists turning this into a grand philosophical comfort. He would not say, "Time bends so that everything is ultimately meaningful," or anything of that sort. He stayed much closer to the ground. The fact, as he saw it, was that experiments forced us to treat time and space as malleable in very precise ways. The consequence was that the speed of light could stay fixed without contradiction. Beyond that, we can speculate, but we should be honest about the boundary between speculation and tested structure. If you sit with this for a while, late at night, the emotional effect is ambivalent. On one hand, the loss of absolute time can feel like a diminishment. There is no single grand clock, no cosmic present in which everything participates. On the other hand, there is a kind of quiet beauty in the way the universe arranges itself so that every local observer can rely on their own measurements and still be part of a coherent whole. On the scale of a human life, these effects are tiny. When you walk to the kitchen, your time does not noticeably dilate. When you ride a bicycle or drive a car, your rulers do not obviously shrink, but the same rules that govern jets and satellites and particle beams also govern your body, your thoughts, the light from your screen to your eyes. You live in a world where time is willing to bend slightly, all the time. to keep the deeper invariance intact. Seen through Feynman's lens, that bending is not an act of mercy or cruelty. It is simply how this particular universe holds itself together. The picture becomes sharper when you stop thinking in metaphors about bending time and start asking, in Feynman's blunt way, all right, but what happens when you actually push on something? In everyday life, the rule seems obvious. You apply a force to a car. It speeds up. Double the push. Roughly double the gain. A rocket burns more fuel. It climbs faster. Nothing in that experience hints at a wall ahead. It all feels linear and negotiable. Give me a big enough engine and enough patience, and surely I can just keep adding speed. Relativity takes that simple intuition and slowly turns it inside out. In the relativistic picture, you can still talk about energy and momentum, about pushing and speeding up. But the relationships are no longer simple straight lines. As an object with mass moves faster and faster, the amount of energy required to produce the same small increase in speed grows. Near the speed of light, that cost does not merely become large, it diverges. The curve that once looked like a gentle hill steepens into a cliff. Feynman liked to think of this in terms of inertia, the stubbornness of matter when you try to change its motion. At low speeds, the inertia of a given object is well described by its rest mass. That is the quantity you implicitly deal with when you lift a box or push a cart. In relativity, however, the effective inertia is tied not just to mass at rest, but to the total energy of the moving object. The faster it goes, the more energy it carries, and the more it resists further acceleration. You can phrase this in different ways. Some older textbooks talk about mass increasing with speed, though many modern physicists prefer to say that mass stays the same and energy and momentum grow in a way that makes the object harder to accelerate. Either way, the practical consequence is the same. When you approach the speed of light, the resistance to further speed up becomes enormous. Imagine a graph with speed along one axis and the energy required to reach that speed along the other. In a Newtonian world, that graph would be a smooth, gently rising curve, always climbable with enough effort. In the relativistic world, the curve behaves differently. At modest speeds, it still looks sensible, but as you approach the speed of light, it begins to rise, almost straight upward. To reach the exact speed of light, you would need to climb an infinitely tall wall of energy. Feynman liked this picture because it made the phrase "cannot reach light speed" feel less like a decree from outside and more like a simple consequence of the way the world accounts for energy. You do not hit a magic barrier where nature suddenly says no. You just find that the cost of gaining the last tiny sliver of speed keeps increasing without bound. No finite engine, no finite fuel, no finite star can pay that bill. This is not just a matter of theoretical curves on paper. Particle accelerators have been pressing against this pattern for decades. Take protons in a large circular accelerator. Engineers and physicists pump energy into them through carefully timed electric fields. Each time the protons go around the ring, they receive another push. The goal is to make them move as fast as possible so that when they collide, the energy concentrated in the impact can create new particles and probe deeper levels of structure. As the energy increases, the proton's speed creeps closer and closer to the speed of light. But something counterintuitive happens. You can keep feeding them more and more energy, and their speed still approaches, but never equals that cosmic limit. The extra energy goes into increasing their momentum and their ability to produce new particles in collisions, not into making their velocity surpass light. If you calculate how close they get, you find numbers that are absurdly near the speed of light, differing by tiny fractions. But near a limit like this, those tiny fractions are where all the difficulty lives. Each new step closer costs disproportionately more energy than the last. The accelerator becomes a monument to diminishing returns in velocity. Feynman would look at these machines and say, with some satisfaction, that they are our most persuasive, practical answer to the question, what stops you? It is not a lack of imagination. It is not a rule printed somewhere in the sky. It is the way energy, mass, and motion are tied together in a self-consistent structure. There is another way to see this wall that Feynman found appealing. because it connects back to the geometry of space-time. Recall the picture of each object moving through space-time with a fixed overall budget of motion, divided between space and time. At low speeds, almost all of this motion is directed along the time axis. You move steadily forward in time and only slowly through space. As you accelerate, you tilt your path, devoting more of your motion to changing position and less to advancing through time. From this viewpoint, the speed of light corresponds to the extreme case, where all of the motion is directed through space and none through time. An object moving at light speed experiences no passage of proper time between events along its path. For a photon, in this simplified picture, emission and absorption are separated in space, but not in its own sense of elapsed time. If you start with an object that has mass, though, its path through space-time cannot be tilted all the way onto the light-like direction. There is always some component of its motion left along the time axis. That is another way of saying that it always has some proper time ticking along its world line. To push it into the light-like path would require eliminating that component, which in turn would demand infinite energy in the relativistic accounting. The geometry and the energy story are the same story seen from two angles. One says, you cannot rotate a time-like world line into a light-like one without tearing the structure. The other says, you cannot boost a massive object to light speed without supplying infinite energy. Feynman liked to emphasize that these are not separate conspiracies. They are two faces of the same constraint. There is a kind of quiet elegance in the way the universe partitions its particles. Those with strictly zero rest mass, like photons, must always move at the speed of light in vacuum. They have no choice. They cannot slow down to join us in the slower lanes. Those with any non-zero mass, however tiny, must always move at speeds less than light. They can get arbitrarily close, but they can never cross over. This partition is not arbitrary. It keeps causality clean. Signals carried by massless particles trace the outer boundary of what can influence what. Massive particles and complex systems like us must live inside that boundary. Our experiences, our technologies, our histories all unfold at speeds that respect that limit. When science fiction stories imagine ships going to light speed as if it were a gear you can shift into with a sufficient roar of engines, they are importing a Newtonian mindset into a relativistic world. In that mindset, every speed is in principle attainable, given enough thrust and strong enough materials. The only obstacles are engineering and funding. A Feynman-flavored response would be gentler but firm. You can solve engineering problems. You cannot repeal the structure embedded in space-time and energy. The wall of infinite energy is not a challenge put there to test your ambition. It is part of the definition of the arena in which ambition can play at all. Even with all this, it is easy to misunderstand the meaning of cannot reach light speed. It might sound, at first, as though the universe is fundamentally conservative, always resisting large changes. But what relativity shows is almost the opposite. As you pour energy into a system, the universe is quite willing to let strange and dramatic things happen. Time dilates. Lengths contract. The mass energy of particles grows and can be converted into entirely new forms in collisions. Entire new particles can appear for a fleeting moment out of the concentrated energy. In that sense, the universe is extremely generous with what it lets you do with finite energy. What it refuses to allow, gently but absolutely, is the particular move of pushing a massive object to exactly the same speed as the field quanta that mediate interactions. One way Feynman might phrase this is that the universe protects the distinction between matter and light-like signals. If a massive object could move at light speed, then in the geometric language of relativity, its world line would blur into that of a causal signal. The clean separation between carriers of information and the things being informed would begin to erode. There is also a connection here to instability. If it were ever possible to accelerate a massive particle to light speed and beyond, the existing formulas for energy and momentum would break down. You would need new rules. Those new rules would almost certainly have to deal with violations of causality, because speeds faster than light allow, in some frames of reference, effects to precede their causes. The wall of infinite energy is, in that sense, not just a technical inconvenience. It is a barricade in defense of a coherent order of events. Feynman, with his taste for fundamental questions, would not claim that we know for sure that causality is preserved at every scale in every corner of the universe. Quantum field theory, the framework he helped build, respects relativistic causality in its core structure. Fields do not transmit influences outside the light cone, yet there are still puzzles at the intersection of quantum mechanics and gravity, places where our theories are incomplete. What he would insist on, though, is clarity about what we can state with confidence today. Within the domains where special relativity and quantum field theory have been tested, the rule that massive objects cannot reach light speed is as solid as anything we know. It is tied into conservation laws, into the detailed behavior of particles in accelerators, into the stability of atoms, and the propagation of forces. There is an existential side to this, if you let it sink in. We spend much of our lives under the illusion that barriers are always circumstantial. If you do not have enough money, earn more. If a path is blocked, look for a detour. If something is too slow, invent a faster method. The story of technological progress seems to back this up. Then physics, spoken in Feynman's unromantic tone, offers a different category of barrier. Not a challenge, not a delay, but a structural limit. No matter how much energy your civilization harnesses, no matter how ingenious your technology becomes, you cannot take a ship made of atoms with non-zero mass and accelerate it to the exact speed of light in a vacuum. The equations that describe acceleration and energy would explode before you arrived. Seen in a certain mood, that is deflating. It takes a cherished fantasy and pares it down. But it can also be strangely clarifying. It tells you that the space of genuine possibilities is a little smaller than unbounded imagination suggests, and that within that smaller space, you can think more sharply. Feynman's style of existential honesty would push that further. If there is a wall of infinite energy ahead, then the interesting question is not how to break through it, but how to live and think, given that it is there. How do you design experiments, technologies, and even metaphors that stay within the domain where your equations make sense? You do not have to like the answer. The universe does not negotiate, but you can take a certain quiet pleasure in the fact that we have learned enough about its structure to know where that negotiation ends. Seen from another angle, that wall of infinite energy is not a cliff at the edge of motion, but a sign that we have been counting the wrong thing all along. We keep staring at speed through space, while the universe seems to be keeping its books in space-time. One of the pictures physicists sometimes use, and that Feynman enjoyed for its simplicity, goes like this. Every object, every person, every particle is always moving at the same overall rate through space-time. Not through space alone, not through time alone, but through the combined fabric. That fixed rate is the speed of light. At first, that sounds wrong. You are sitting still, perhaps lying in bed listening to this. You are not moving at anything like the speed of light. Your position in space is not changing much at all. How can you be moving at that rate? The trick in this picture is that your motion is almost entirely along the time direction. When you are resting on your chair, your coordinates in space hardly shift, but your time coordinate steadily increases. In that sense, you are racing forward in time at the maximum allowed pace, devoting your entire motion budget to becoming older. When you begin to move through space, that motion budget has to be shared. A small portion is reallocated from the time direction to the spatial directions. You still move through space-time at the same overall rate, but some of that motion now shows up as changing your location, because the total cannot exceed the speed of light. The more you spend on space, the less you have left for time. This is just another way of talking about time dilation. From the point of view of someone watching you speed by, your clock ticks more slowly. You are using part of your fixed space-time motion to change your spatial coordinates. so your progress along the time axis is proportionally reduced. In the extreme limit, if something could move through space at the speed of light, all of its motion would be allocated to the spatial directions and none to the time direction. Its path in space-time would be completely tilted over. In that picture, no proper time would pass for it between its emission and its absorption. The idea of how long the journey takes would lose its usual meaning. Massless particles, like photons in vacuum, are forced into that state. They have no rest mass, no internal clock that ticks in the usual sense. Their world lines in space-time are light-like, skimming along the boundary between what can send signals to you and what cannot. They are the pure expression of the maximum motion budget spent entirely on space. Objects with mass are different. They are stuck with time-like world lines, paths that always retain a component along the time direction. They cannot tilt all the way over to align with light-like paths. That geometric fact and the energy wall from the previous chapter are two descriptions of the same underlying limitation. Feynman liked this budget picture because it turns a prohibition into an accounting rule. Instead of thinking, "The universe forbids me from going faster than light," you can think, "The universe insists that my total motion through space-time be equal to the speed of light. And because I have mass, some of that must always be reserved for time." Once you adopt that picture, several otherwise puzzling phenomena slot into place with a kind of quiet inevitability. Take the story of muons in the atmosphere, which Feynman enjoyed as a teaching example. Muons are unstable particles created when cosmic rays slam into atoms high above the Earth. In their own rest frame, muons live only for a tiny fraction of a second before decaying. If you imagine them as Newton would, created at many tens of kilometers above the surface and traveling at high speed downward, they simply do not have time, in the classical sense, to reach the ground. They should mostly decay long before they get anywhere near you. Yet experiments show that many of them do reach detectors on the surface. That is a fact, not an interpretation. The count of muons at ground level is far too high to be explained without relativity. From the ground observer's frame, the explanation is time dilation. The muons are moving so fast through space that their clocks run slow compared to clocks on Earth. A lifetime that would be brief if they were at rest stretches out when they are hurtling toward us, allowing them to survive long enough to traverse the distance. From the muon's point of view, you can tell an equivalently correct but differently flavored story. In its rest frame, its internal clock is ticking at its normal rate. It still decays after the same proper time as always. What has changed is the thickness of the atmosphere. Because the muon is rushing through space-time at a large tilt relative to the Earth frame, the length it sees between its creation point and the ground is contracted. The journey is shorter than we would measure from the surface. It can make it to the ground before it decays, because in its frame, there simply is not as far to go. The two descriptions, one in terms of slower time, the other in terms of shorter distance, are not contradictory. They are different ways of slicing the same space-time. Underneath them both is the same budget rule. The muon, like everything else, moves through space-time at the speed of light. How that motion is apportioned between space and time depends on the frame. This is exactly the kind of thing Feynman had in mind when he talked about the character of physical law. A good theory gives you a single, coherent structure from which apparently different stories emerge as special cases. Relativity's space-time budget is such a structure. It lets you understand time dilation, length contraction, and the energy wall as different faces of a single geometric fact. The budget picture also reframes the question of why faster-than-light travel is problematic. In a Newtonian world, you might think of speed as something you can always add to. Start with a bit of motion, add more, and so on. The limit, if any, is just a matter of engineering. In the space-time view, you already start at the maximum. The moment you exist as a physical entity, you are committed to speeding through space-time at the speed of light. The only choice is how you split that motion between time and space. You cannot make the overall vector longer. There is no room to add more speed. The most you can do is redirect it. That is what acceleration really is in this picture. A rotation of your space-time velocity, tilting it so that more of it points along space and less along time. There is an existential echo here that Feynman himself rarely indulged in directly, but that sits not far beneath the surface. If your motion through time is part of a fixed budget, then in a sense, your lifespan is the record of how you have spent that allocation. You cannot increase the total amount of motion existence grants you. You can only choose the path along which you spend it. Phrased that way, the analogy becomes imperfect. You cannot decide, in any straightforward way, to trade years of your life for extra spatial speed, beyond the tiny trade-offs that relativity already enforces in extreme situations. But as a metaphor, it catches something about the finiteness of both physical and personal possibilities. There is only so much change you can undergo, only so many paths you can trace through the shared space-time before your particular world line ends. Feynman would probably warn against drawing too much comfort or despair from this. The point, in his philosophy, is not to turn physics into a moral tale, but to appreciate the clarity of what has been discovered. The universality of the space-time speed budget is one of those clear things. It also pushes back, gently but firmly, against a certain kind of technological optimism. There is a habit, especially in stories about the future, of treating constraints as invitations. Gravity is a problem? Invent anti-gravity. Light speed is a problem? Invent warp drive. The obstacles of today are reimagined as the raw material for tomorrow's triumphs. Relativity does not exactly crush that spirit, but it does define a horizon past which that kind of thinking has no foothold. Within the space-time budget rule, you can warp and bend the geometry, as general relativity allows. You can imagine curving space-time so that paths which look like shortcuts appear, as in speculative discussions of wormholes. But you cannot, within the tested form of the theory, make a local object outrun the limit by simply stepping harder on the accelerator. The budget is not yours to expand. Feynman's respect for this kind of limit shows up in his attitude towards speculation. He was open to wild ideas, but always with the caveat that they must, in the end, be tested against the existing structure. A proposal that violates the space-time speed budget without providing a new and consistent framework is not just daring, it is incoherent. One of the things that separates physics from myth in his view is that physics accepts, at certain points, that the structure itself is the explanation. Asking why the budget is what it is, at a deeper level, is like asking why the space-time interval has the particular signature it does, or why the speed of light takes the numerical value it does in human units. At some stage, the honest answer is that we do not know. We only know that if those features were different, many of the successful predictions of our current theories would fail. The space-time budget picture, then, is not a final metaphysical truth. It is a way of organizing a remarkable collection of empirical facts, that all massless entities we have observed travel at the same fixed speed in vacuum, that all massive entities travel more slowly, that time and distance adjust so as to preserve certain invariants, that causal influences respect light cones. Put together carefully, those facts ask to be seen as manifestations of a single underlying rule. When you accept that rule, the sentence, "Nothing can travel faster than light," stops sounding like an arbitrary constraint. It becomes a shorthand for a whole geometry of existence, in which everything that happens is a rearrangement of a fixed velocity through space-time, never a transcendence of it. It is tempting, at this point in the story, to look for a loophole. Perhaps there is some way of moving the stage itself, of sliding space-time under an object so that, in some larger sense, it moves faster than light without locally violating the budget. Ideas along these lines appear in the literature, often with names that sound like they come from science fiction episodes. They exploit the fact that general relativity allows space-time to curve and stretch. In principle, regions of space can recede from each other faster than light because the budget applies locally to motion through space-time, not to the expansion of space-time itself. Feynman, were he here to comment, would likely remind us of two things. First, that such speculations remain untested and run into immense practical and theoretical difficulties. Second, that even if some of them turned out to be physically realized, they would still have to respect the local structure we have been describing. The budget rule, as far as we know from countless experiments, is not negotiable on small scales. So, we are left with a universe that is, in a precise sense, always in a hurry. Everything is rushing along at the speed of light in space-time. The fact that you do not feel this is a matter of how that rush is divided. You experience mostly the flow along time, the slow drift through space that marks an ordinary human life. The extraordinary phenomena we have been discussing arise when that division is pushed to extremes. Seen that way, the limit on speed is not a ceiling pressing down on you. It is the shape of the corridor you are already running through, whether you notice it or not. Once you see speed as a fixed budget through space-time, another question quietly appears underneath it. Not how fast things can move, but how fast reasons can become consequences without the whole story coming apart. Physics, at least in the form Feynman respected, is not only a catalogue of events. It is a discipline that cares about order. Not moral order, not narrative satisfaction, but the simple question of what can possibly influence what. A cause should come before its effect in any frame that can actually test that relationship. If that basic demand is violated, the language of explanation itself starts to crumble. Relativity gives a very clean way to think about this. Around every event in space-time, you can draw a structure called the light cone. Imagine the event as a point. The future light cone consists of all the events that can be reached by signals moving at the speed of light or slower, starting from that point. The past light cone consists of all the events that could have sent such signals into that point. Everything else, outside both cones, is too far away in space and too close in time to be connected by any slower than light signal. This is not just geometry for its own sake. It is a map of what can possibly be a cause and what can possibly be an effect. If an explosion happens here and now, the future light cone marks the region in which anything could be singed, shaken, or informed by that explosion. The past light cone marks the region in which anything could have contributed to causing it. Events outside both cones are simply too remote and too oddly arranged in space-time to have any direct relationship. They are elsewhere, in a strict sense. When physicists say that nothing can travel faster than light, hidden inside that sentence is another. Nothing can carry information from one event to another outside the light cone. No influence, no signal, no message, no chain of physical interaction can jump that gap. In this sense, the speed of light is the speed of causality. Feynman liked to protect this connection between speed and story. He understood that if you tamper with the light cone, you are not just editing a number in an equation. You are editing the set of stories the universe can tell without contradicting itself. Consider a simple thought experiment that appears in many relativity textbooks, and that Feynman would have treated with a mixture of amusement and seriousness. Imagine a long spaceship floating in deep space, far from gravitational fields, moving at a constant high speed relative to some distant observer. At the front of the ship is an astronaut, at the back another. In the ship's own frame, their clocks are synchronized. They agree on what it means for two events to be simultaneous. Now suppose that the astronaut at the back sends a hypothetical signal that travels faster than light along the ship to the astronaut at the front. In the frame of the ship, the signal goes forward, faster than any light pulse could, and arrives a moment later. So far, so speculative. But relativity tells us that simultaneity is not absolute. An observer moving relative to the ship slices space-time differently into nows. For that observer, the order of events can change. A careful calculation using the Lorentz transformations shows that there are always frames in which a faster-than-light signal would be seen as arriving before it was sent. If you then allow the astronaut at the front to send a reply, also faster than light, back to the rear, you can engineer a situation in which, in some frame, the reply arrives before the original message was sent. You could, in principle, send yourself a note that says, "Do not send the note." If you obey your own instruction, the note is never sent. If it is never sent, there is nothing to warn you, and so you send it. The story eats its own tail. This is the famous family of paradoxes, in which people imagine assassinating their own grandparents before their parents were conceived, or sending stock tips to themselves in the past. They are not just puzzles for time travel enthusiasts. They are signals that something is structurally wrong with the assumption that you can have faster-than-light communication in a relativistic space-time and still keep causality neat. Feynman had a strong nose for this kind of inconsistency. To him, paradoxes of this sort were not invitations to mystical speculation. They were red flags. If your theory allows you to build a machine that can, according to the same theory, undermine the notion of cause and effect, then the theory in that form is not acceptable. There is a subtlety here, though, and it is one he appreciated. In the mathematics of quantum field theory, some particles are sometimes described as if they move backward in time. In Feynman diagrams, the graphical shorthand he introduced, certain lines can be interpreted either as particles traveling forward in time or as antiparticles traveling backward in time. The two views are equivalent in the mathematics. But this is not a license for signals that violate causality. The backward-in-time interpretation is a calculational device, an alternative way of organizing the same amplitudes. The underlying theory still respects the condition that measurable influences do not travel outside the light cone. The probabilities for outcomes in any experiment are such that no chain of operations by observers can send a controllable message into their own past. That distinction mattered to him. He loved using imaginative pictures to understand equations, but he insisted that those pictures be disciplined by the demand that no actual procedure for manipulating the world contradict the causal structure enforced by relativity. There have been moments in the history of modern physics when nature seemed to flirt with violating that structure. In the year 2011, a collaboration called Opera, working with neutrinos sent from a facility near Geneva to an underground detector in Italy, announced a baffling result. The neutrinos, according to their first analysis, appeared to arrive slightly earlier than a light beam would have taken to travel the same distance through empty space. The difference was tiny, measured in tens of nanoseconds, but the implications were enormous. For a brief period, much of the physics community was deeply unsettled. If the result were correct, it would threaten the very fabric of special relativity, and therefore much of quantum field theory. The people involved were careful and sober. They did not rush to declare relativity dead. They asked for help, for independent checks, for criticism. The episode is almost an ideal case study in the Popperian spirit Feynman admired. Many groups tried to replicate or challenge the measurement. Some examined the synchronization of clocks. Others checked the statistical methods. Eventually, the Opera team themselves found issues with a loose cable and with the timing system. Reanalyses showed that, within experimental uncertainty, the neutrinos did not in fact outrun light. For a while, though, the idea had to be taken seriously, if only to be properly killed. That seriousness was not driven by a love of sensational possibilities. It was driven by a clear appreciation of how deeply the speed of light limit is embedded in our theories. To accept faster than light, neutrinos would not be like discovering a new particle in an empty slot. It would be more like discovering that two fundamental axioms of arithmetic are in conflict. Feynman, had he lived to see that episode, would probably have smiled at the way it resolved. Not out of smugness, but out of relief that the coherence of the structure held firm under pressure. And also, perhaps, out of respect for the experimenters, who were honest enough to share an alarming result and willing enough to help dismantle it when evidence went against it. The idea of tachyons, hypothetical particles that always move faster than light, belonged to an earlier era of speculation. They appeared as mathematical possibilities in certain equations. If you allow mass squared to be negative in the formulas of relativity, you obtain entities that can never slow down to light speed. Just as ordinary massive particles can never speed up to it, but always remain above it. The temptation to treat these mathematical ghosts as physical objects was strong in some circles. From a causal point of view, however, tachyons are poison. If they could carry information, you would again be able to set up scenarios in which signals go outside the light cone and causality loops emerge. Most physicists came to view tachyons as indications that a given theory is unstable or badly posed. If they appear, the theory needs to be reworked until they are gone or reinterpreted in a way that does not allow violations of causality. This is one of the reasons modern quantum field theories are built with a deep respect for Lorentz invariance and causality. The commutators of field operators vanish for space-like separations, which is a technical way of ensuring that operations performed in regions that cannot be connected by slower-than-light signals do not influence each other in measurable ways. It is a formal expression of the simple idea that you cannot poke the universe over there and have it squeal over here faster than a light signal could have traveled. When Feynman talked about quantum theory and relativity, he did not present this as a constraint added awkwardly on top of the mathematics. It is baked into the construction. The very amplitudes that describe how particles scatter are arranged so that the resulting probabilities never permit a controllable influence outside the light cone. The speed of light, in that role, is not merely a property of photons. It is the slope of the boundary within which all consistent stories about cause and effect must be drawn. There is a curious contrast between this strictness and the looser way we often think about stories in everyday life. We routinely imagine what would have happened if something earlier had gone differently. We wonder what tiny message to our past selves would have changed our careers, our relationships, our regrets. Our culture is full of tales in which a character travels back and alters a key event, watching reality reorganize itself around the new fact. Physics does not forbid us from imagining those things. It does, however, suggest that the universe we inhabit does not implement them. The rules by which fields interact, by which particles propagate, by which information is carried, all conspire to prevent the construction of machines that would turn those counterfactual fantasies into actual loops. In that sense, the speed of light is a kind of editor. It forbids certain plot twists, not because they are narratively unsatisfying, but because if they were allowed, the difference between story and contradiction would evaporate. Feynman, wary of grand philosophical pronouncements, would likely resist turning this into a metaphysical statement about free will or destiny. His point would be narrower and more precise. The demand that causes precede their effects in any experimentally meaningful frame is a condition for doing physics at all. Without it, the idea of prediction loses its footing. You could observe a phenomenon and never be sure whether some later choice by some distant agent would retroactively change its explanation. By tying the speed of causality to the speed of light, relativity gives physics a solid floor. It does not tell you which events will happen. It does not tell you why the universe exists, but it tells you that, within this universe, there is a consistent way to say that this event could have influenced that one, and that some other event, out of reach beyond the light cone, could not have. There is a gentle existential consequence hidden in that clarity. It means that, for any given event in your life, there is a finite region of the universe that could have played a direct physical role in bringing it about. The rest, however emotionally entangled it may feel, is outside your past light cone. It is elsewhere. In the precise, technical sense, we do not usually think that way. The boundaries of our perceived causality are psychological, not geometric. Yet in the background, every decision, every accident, every conversation is threaded through by a strict geometry of influence that respects the same limit that stops rockets and particles from outrunning their own light. When people say that the speed of light is the ultimate speed, they are often picturing a race. It is more accurate, in Feynman's quiet style, to say that it is the outer edge of a web. Inside that web, stories can unfold in many ways. Outside it, there are events that exist, but not as parts of your chain of cause and effect. The fascination with faster-than-light travel is, in part, a yearning to throw a rope over that edge and pull distant possibilities into our nets. Physics replies, not with scorn, but with a kind of patient refusal. The equations that have survived every test we have thrown at them seem to say that such ropes would tangle the web beyond repair. So when we insist that nothing can move faster than light, we are not only safeguarding a constant in Maxwell's equations or a term in a Lagrangian, we are also safeguarding the possibility of telling coherent stories about the world. Stories in which effects follow causes, and not the other way around. It is easy to talk about light cones and causality on a blackboard. It is harder, and somehow, more moving, to watch the same ideas quietly keeping airplanes on schedule, images sharp in hospitals, and satellites honest in their orbits. Feynman had a simple rule for himself. A beautiful theory is not enough. Nature has to get a vote. If the speed of light is not just a number but the skeleton of cause and effect, that fact should leak out everywhere into devices that never once used the phrase space-time. We have already passed through some of the classic experiments in outline. Jupiter's moons arriving late. An interferometer in Cleveland refusing to see the ether. Clocks on airplanes slipping out of sync. In this stretch of the journey, it is worth sitting with how broad and how mundane the evidence has become. Start in a place that feels as far from everyday life as possible. A ring of metal buried under the ground near a small village in Europe. Along that ring, protons are whipped around by magnets, folded back on themselves again and again. Each turn, electric fields give them another shove. Their speed creeps closer to that cosmic limit, the speed of light in empty space. By the time they are ready to collide, they are moving so close to that limit that, if you wrote down the difference as a fraction, it would be a string of nines and only then a deviation. If the world were Newtonian at those scales, adding energy would simply push speed higher and higher. There would be nothing special about the speed of light except that it happens to be large. What accelerators actually show is something else. The energy stored in each proton grows dramatically as the machine works harder. The ease with which their paths can be bent shrinks, yet their speed barely changes in the last stages. The extra energy feeds mass energy and momentum, not the meter per second count. That is a direct, precise, endlessly repeated demonstration that the speed of light is a ceiling for objects with mass. It is not a slogan. It is an engineering constraint for some of the most complex machines humans have ever built. Shift now to the upper atmosphere. Cosmic rays crash into atoms, producing showers of secondary particles. Among them are muons, whose lives, in their own rest frame, are very short. If you take their lifetime, multiply by their speed, and ask how far they could travel before decaying, the answer, in a classical world, is not very far. Certainly not from the high altitudes where they are born all the way down to sea level. Detectors on the ground tell a different story. They register a flux of muons much higher than those naive calculations would allow. The only way to reconcile those counts with the known decay rate is to accept that time for the muons is not the same as time for us. Moving so fast, the clocks along their world lines tick more slowly relative to Earth's. The space-time budget we talked about earlier is on full display. They spend more of their motion on space, less on time, so more distance can be covered before their internal processes run out. The same effect has been probed in controlled settings, with beams of unstable particles in accelerators. The lifetimes of those particles stretch as their speed increases, exactly in line with the formulas of special relativity. The simple, cold statement that no object with mass can reach the speed of light comes bundled with those more subtle predictions that time itself will soften and stretch for the traveler. Feynman liked these particle stories because they compressed the whole edifice into a single line of reasoning. Start with the invariance of the speed of light. Accept the geometry of space-time that respects that invariance. Derive time dilation and energy growth with speed. Then look out into the world and see muons, mesons, and protons all behaving as if the equations were written into their bones. But you do not need a ring of magnets or a rain of cosmic particles to feel the speed of light limit pressing in. It is there in the way your phone knows where you are. The global positioning system is a swarm of satellites, each carrying an atomic clock and circling Earth along a carefully chosen path. Each satellite broadcasts its time and position. A receiver on the ground listens to several at once and infers its own location from the tiny differences in signal arrival times. The geometry is simple in principle, draw spheres around each satellite with radii equal to the speed of light times the travel time of the signals, and the intersection point is U. The catch is that those atomic clocks on the satellites do not tick in unison with an identical clock on Earth's surface. Special relativity says they run slightly slow because they are moving relative to the ground. General relativity says they run slightly fast because they are farther from Earth's mass and feel a weaker gravitational pull. The two effects are comparable in size but do not cancel. The net result is that, if uncorrected, satellite time would drift away from ground time by tens of microseconds each day. Tens of microseconds may sound small. Multiply that by the speed of light and it becomes a drift in position of kilometers. A navigation system left to ignore relativity would, within a day, tell ships and planes and hikers that they were somewhere else entirely. So the designers did not ignore it. They built the corrections into the very definition of satellite time. The clocks in orbit are set to tick slightly slow on the ground, so that once they are aloft, and relativity does its work, they match a standard on Earth. Receivers in your pocket perform additional adjustments when they process the signals. Every time you watch a little blue dot move along a map, you are living inside a web of devices that all respect the same speed limit and the same bending of time that Feynman talked about on blackboards. The theories are not sitting in a museum. They are in the chips and antennas. Move from phones to hospitals. Magnetic resonance imaging machines rely on the behavior of atomic nuclei in strong magnetic fields. They also rely on precise timing and on the interactions of fields that propagate at the speed of light. The equations used to design and calibrate those machines are deeply relativistic. The safety margins and pulse sequences assume that fields do not send influences faster than light through the tissues they probe. When you lie inside one of those devices, listening to it clatter and hum, the images being built of your brain or spine are downstream from the same constants that keep neutrinos in line and satellites honest. Synchrotron radiation, the powerful light emitted when electrons are bent along curved paths at high speeds, is another place where the limit shows itself. Electrons in storage rings radiate in tight beams, whose patterns and energy distributions match the predictions of relativistic electrodynamics. If electrons could quietly slip past the speed of light, those patterns would be different. The brightness and focus of synchrotron beams, now used for studying everything from protein structures to advanced materials, would not line up with theory. In practice, they do. The limit is written into each photon of that intense light. Feynman had a special affection for experiments that treated theories harshly. In his reading of Karl Popper and in his own sensibility, a strong theory is one that forbids many possibilities and survives attempts to catch it in a lie. The speed of light limit has been subjected to that kind of scrutiny. Astronomers have looked at the arrival times of high-energy photons from distant cosmic explosions. If different energies of light had slightly different maximum speeds, or if some obscure mechanism allowed high-energy particles to outrun low-energy ones by even a tiny relative amount, the fronts of those bursts would smear out over the millions or billions of years they travel. Instead, within the resolution of our detectors, the sharpness remains. The variations seen are consistent with the violence at the source, not with energy-dependent violations of the light speed limit. In laboratories, people have sent entangled photons through different media, played games with group velocities and pulse shapes, and announced superluminal effects. Each time, when examined carefully, the results turn out not to allow information to be sent faster than light. The peaks of wave packets can be distorted and pulled forward. The shapes of pulses can be reshaped, but the front of any signal that carries new information still respects the light cone. The deeper analysis always finds the same thing Feynman insisted on. No usable influence crosses the boundary. Even gravity, which in Newton's time was thought of as acting instantaneously at a distance, has been brought into this web. General relativity predicts that changes in gravitational fields propagate at the speed of light, carried by ripples in spacetime. When observatories recently began to register gravitational waves from colliding black holes and neutron stars, the arrival times of the gravitational signal and any accompanying light pulses could be compared. Within very tight margins, they match the prediction that gravity waves and light share the same limit. The point of rehearsing this variety is not to drown you in technical details. It is to make it hard to see the speed of light limit as a fragile description. It has been tested with particles and planets, with clocks and circuits, with astronomical distances and human-scale devices. Each new domain is an opportunity for the universe to disagree. So far, it has not. Feynman, with his reluctance to treat any principle as sacred, would take that seriously. He would say, as he often did, that our confidence is not based on any authority, but on a track record. The speed of light limit has exposed itself to some of the most diverse and precise tests we have managed to invent, and it has not obviously cracked. That makes it one of the sturdier pieces of the current framework. He would also, in the same breath, remind us that this sturdiness is conditional. It holds until and unless an experiment finds otherwise. If some future measurement of gravitational waves, or some next-generation accelerator, or some unexpected astrophysical observation found a clear, reproducible violation, the honest response would not be to deny the data. It would be to recognize that one of the pillars we have been leaning on has shifted, and that a new structure will have to be built. In that sense, the real-world proofs we have been walking through are not arguments that the speed of light limit is eternally true. They are arguments that, as of now, any claim to overturn, it has to be prepared to face not just a single cherished experiment, but an entire ecology of devices and phenomena in which that limit is already doing quiet work. There is something quietly humbling about that. We like to think of deep principles as living in equations on a page, or in the mouths of famous scientists. Here, the principle lives in the way your navigation app draws a route, in the reliability of a medical scan, in the pattern of cosmic rays that reach a detector on a mountain. Feynman's way of putting it would be plainer. The world is what it is. Our job is to notice. The fact that so many different ways of noticing have converged on the same light speed limit is, in itself, one of the most astonishing facts about the universe. At some point, when the same limit keeps appearing in telescopes, in colliders, in hospital machines, and in the small glowing rectangle in your hand, the question quietly turns around. It is no longer only, what does this say about the universe? But also, what does it say about us that we were able to notice? Feynman liked to joke and play, but he took that part very seriously. Not the celebration of genius, not the worship of names on the covers of books, but the almost embarrassing fact that a species which evolved to throw stones and gossip in small groups has managed to uncover a rule as unforgiving and abstract as a cosmic speed limit. Think about the chain you have just walked along. A falling apple, a falling moon, tiny points of light around Jupiter running a few minutes late, a pool of Mercury in Cleveland holding up a stone slab while a pattern of bright and dark fringes refuses to move, an obscure patent office worker in Bern who decides to trust those fringes and those equations more than his own intuition about time. Particle beams circling underground, muons that should have died but did not, satellites correcting their clocks so that a map on your phone does not lie. At each step, what matters is not a heroic individual miracle. What matters is a certain kind of honesty about questions. Newton did not have to ask whether the moon was falling under the same law as an apple. Romer did not have to trust the delay instead of blaming his telescope. Michelson and Morley did not have to accept that their beautiful experiment saw nothing. Einstein did not have to give up on absolute time. Experimentalists in the 20th and 21st centuries did not have to keep trying to break a rule that so far has never bent. Yet they did, over and over. People with very ordinary bodies and very limited lifespans pushed one more step past what felt like an acceptable stopping point and asked, as Feynman would say, but what really happens? A cosmic speed limit sounds, at first, like a statement about our lack of power. You cannot outrun this. You cannot send a message that gets there sooner than this. You cannot build a ship that cuts across the stars the way a boat cuts across a lake. It can feel like the universe is being stingy with possibility. Feynman's last lesson, if you listen closely to the way he spoke about these things, is stranger and softer. The speed of light limit is not there to frustrate your ambition, It is there to make a world like this possible at all. Without a fixed maximum speed for influence, there would be no consistent way to decide what caused what. Without the bending of time and distance to protect that speed, there would be no way for different observers to agree on the results of an experiment. Without the wall of infinite energy in front of light speed, you could accelerate matter into a regime where your own equations contradict themselves. A universe without that limit is not a place where you simply travel faster. It is a place where explanation itself begins to fall apart. Seen that way, the limit is not an arbitrary fence. It is part of the definition of reality as something that can be known, argued about, and shared. Feynman was suspicious of any sentence that began with, "The universe wants." He would not say, "The universe gives you this ceiling so that you will be humble." He would say something plainer, "The universe appears to have this structure. From that structure, many consequences follow. If you want to live in a world where cause and effect make sense, this is the kind of structure you need." The humility enters on our side. We are used to thinking of understanding as a kind of mastery. Once you know the law, you can control the phenomenon. Learn aerodynamics, and you can build planes. Learn chemistry, and you can synthesize drugs. Learn electronics, and you can etch information into silicon. It is tempting to put the speed of light into that same category, something to overcome once we understand it deeply enough. What Feynman's way of looking does is quietly reverse the direction. The more you understand this particular law, the more you see that it is not an obstacle in front of you, but a foundation beneath you. You do not stand outside it, manipulating it. You exist as a pattern of matter and fields already bound by it. The light from the screen in front of you is trapped by that limit. The signals in the cables under the ocean are trapped by it. The neurons in your brain, the electrochemical storms that make your thoughts, live in the same web. When you think about the universe, when you question it, when you argue with it, you are doing so from inside the geometry that the speed of light helps define. There is a kind of quiet comfort in that, if you want it. But you do not have to turn it into a spiritual message. It is enough to notice the honesty of the situation. You are small, and you are not in charge of the rules, and yet you have managed to read some of them with surprising clarity. Feynman also reminds us not to claim more than we have earned. We do not know why the speed of light has the numerical value it does in the units we have chosen. We do not know why space-time has exactly the properties it has, instead of some other nearly imaginable set. We can say that if those things were different, the world would be unrecognizable. But beyond that, we reach the place where the ladder of why runs out of rungs. "You can know what happens," he once said in another context, "without knowing why it happens that way." For him, that was not a failure. It was a kind of freedom. You are allowed to stop at structure. You are allowed to say, "This is as far as honest physics can go today." And beyond this is speculation or poetry. The speed of light, in that sense, is a teacher of restraint. It shows you a wall that is not negotiable, and in doing so, it invites you to focus your creativity on what is possible inside it. Instead of dreaming about signals that outrun causality, you can dream about better ways to use the finite signals you already have. Instead of fantasizing about visiting distant galaxies in a heartbeat, you can think about what it means to be a creature whose whole civilization fits into a small, slowly moving light cone. That might sound like a narrowing. Feynman would probably say it is a sharpening. Limits do not only remove possibilities, they make the remaining ones more precise. Late at night, when you hear the familiar line, "Nothing can go faster than light," you can let it slide past as another piece of trivia, or you can remember what is hidden inside it. Centuries of people refusing to accept lazy answers, the bending of time and space to keep stories consistent, a universe that seems to value coherence, even at the cost of our intuitions. And you can ask yourself a quieter version of the same question we have been asking about speed. Not, "How can I go faster than this?" but, "Given that my life is lived inside this limit, what is actually worth moving toward at all?" If letting that question hang feels like the right way to end, stay with it. If you want to walk further down these paths, with more nights spent unpacking a single sentence from physics until it turns into a mirror, you can stay with this channel, or return to this piece, or share it with someone who will not mind being left with more questions than answers. The limit is not going anywhere. The interesting part is what you choose to understand within it.